So in this case, we are going to consider another question as a continuation from the previous questions that we were working with. So we are not going to waste much time. We are given that these results that we are given here were obtained from tests conducted on a 25 kilowatt. Then we are given it's a 4-pole, 380 50 hertz, three-phase induction motor. So these results are all line values, all these values that you're given. So we have got the no load test and also the logged rotor test. So here there is an advantage because of what we are given in terms of the power factors, all right, for the no load and also for the short circuit. So it was going to be easier for us to determine their corresponding angles. So here, that was going to be the angle. Remember, that is arc cos of what? Of this part that you're given. So meaning to say, our angle was going to give us 82,01. So 82,01, that's approximately 82 degrees, guys, because of the graph part that we're going to need. At least 82 is easier for us to locate that one. Then also you do the same thing for the short circuit cos of this value. That was going to give us 70,001, which is approximately 70 degrees. So that is from the given power factors. So in this case, they also gave us a statement that the motor is a star-connected stator winding, all right? It is a star-connected stator winding with a resistance of, take note of the resistance that will be given. A resistance of what? 0.25 ohms per phase. We are given the phase value for this stator winding that we are given. So in terms of the stator winding, what we are given there is its phase resistance. So we are given the phase value of 0.25 ohms. So that is what we are given there. Using a scale of 1 centimeter to represent 6 amps, draw a circuit diagram and determine the following from it. For this condition, full load condition, take note. So anyways, that is it, guys. Take note, we have got our scale 1 centimeter to represent 6 amps. So that is the one that you're going to use. And the full load condition, we're going to see that one later on. So this part, guys, is just a continuation. We actually referred to this part. We know what we are going to need on our graph. Remember, our reference axis. From that, we are going to need the angle between, that is for the no load, that is between the no load current. But in terms of the vector O to what? To its referred value. So that is it for a no load. So meaning to say, we are going to need the vector O to O bar like this one, which is the current that it represents over the scale. So the no load current, remember, we are given this one, that is 12 amps. And the scale 1 centimeter represents 6 amps. So we're going to divide by 6. So that was going to give us 2 centimeters. All right. So we have got 2 centimeters. Remember, already the angle, we have it. So what we just needed there is the vector that is going to represent our no load current, all right, which is our vector or to its referred value. Then we also have for the locked rotor, test, which is our short circuit. Already the angle we have it. The short circuit angle is there. But remember, we said we are going to need the short circuit current that operates at a normal, assuming that we are dealing with a normal voltage. So meaning to say, what we are going to need is first that value for the what? Short circuit current operating at a normal voltage, which is short circuit current times V rated over V short circuit, which is the test values that we are given. From our test values, remember, for the locked rotor, we've got our short circuit value and also have our V short circuit. The rated value from the properties of the motor that we are given, 380 volts. So meaning to say there everything we have. So our short circuit current, that is 30 amps. Our V rated, remember, that is 380. So we've got 380 over the short circuit voltage here, which is 110. So this is what we're going to have. So that was going to give us 103,636 amperes. That is our corresponding short circuit value for that part of the short circuit. But what we need is the corresponding vector O to A. For that short circuit, we need the corresponding what? The corresponding vector. So remember, our corresponding vector is simply going to be what? It represents the short circuit current value over what? Over the scale. So you're simply going to take the value that we just calculated. Okay, so this one, guys, is just a repetition. Our scale, remember, it was 1:6. So that was going to give us a vector OA, which is approximately 17,3 centimeters. All right, so that was going to give us the corresponding vector there. So this is what you need, guys, and you can just have your graph. So that's 17,3 centimeters, remember, representing what? The part of our short circuit current, assuming normal voltage applied. So with these values, yes, we can have our graph presentation, but let us just finish with this section, because last time we were dealing with a condition where they consider the stator copper loss and the rotor copper loss at standstill being equal. All right, if you still remember this part when we're referring about locating the point E. Say for us to locate the point E, there are conditions that we can be given there. And on the last presentations that we're dealing with, we had the condition, which was the first one, where the stator copper loss must be equal to the rotor copper loss at standstill. But in this case, that is not a concept. They gave us the second condition this time, where we are given the stator's phase resistance. It is given. So whenever you are given the stator's phase resistance, in order for you to determine or to locate the point E, we are going to work with the stator copper loss. From the stator copper loss, we can determine the distance EF. Remember, from E to F, that is the part of what? Stator copper loss at what? A standstill. So the distance null, EF, will be the stator copper loss. Remember, we are dealing with a three-phase. So we are simply saying, guys, our stator copper loss at standstill. All right, at standstill will be given as what? Square root of 3 times the line voltage that we are given times the line current. That is what we are going to be having. Then we must, in this case, multiply by the corresponding. In this case, if you are dealing, let's say, with a vector, because the current now is no longer presented. We are dealing with a vector. So when you are dealing with a vector, we are going to use that vector EF from E to F. Remember, that is the part of our stator copper loss at standstill, E to F. So that is where we're going to have our vector EF. And we have to make that EF the subject because it is going to help us to locate this position of EF. So to find our EF, that is where we're going to make it the subject. We're going to have stator copper loss, whatever that we are given there, over what? Square root of 3 times what? The line voltage, which is this formula that we are given here. But because the presentation that we are seeing wherever EF is must be considered according to the scale, so we must divide everything by the scale. So you must be very careful about this one. So these are the stages that you're going to need. You must determine the stator copper loss from where? From the phase value of the resistance that you're given. Then you determine your vector EF. All right. So let us have that one. Determine first because we've got that phase value for the resistance. So we are going to start by determining the stator copper loss, which is equivalent to 3 times the short circuit current at a normal voltage times what? The phase value for the stator winding. So remember, we calculated this value. It's unfortunate that I erased it, but we calculated this. It was 103,636 squared. All right, so we're going to square that one times the phase value of 0.25. So that's it. That was going to give us 8,000. So we are calculating the stator copper loss from the phase value. Remember, power from the phase value of what? The resistance, okay? So that was going to give us 8,055,315 in watts. This is the one that we are going to need to determine the length of EF. For us to have the length of EF, we're going to use this formula now, stator copper loss over this divided by the scale. We are now determining the exact length for EF. So our EF is going to be the stator copper loss over what? Square root of 3 times the line voltage. Whatever that we are given here, we must divide by what? By the scale. So already the stator copper loss, we determine this 8,055,315, everything over what? Square root of 3 times the line voltage. Remember, that was 380 from the given properties of the motor. Our rated voltage there, 380. All right, so this is it. Whatever that you're going to have here, divide by the scale. 1 centimeter represents what? 6 amperes. 1 centimeter represents 6 amperes. So this is giving us the corresponding vector of what? Of EF, meaning to say, by the moment the scale is applied, we are going to have this as a vector in centimeters according to the scale that we are using. So that was going to give us approximately 2,04 centimeters, all right, which is something like approximately 2 centimeters. That is EF. So this is going to help us whenever we are to have our diagram because we know the length that we have from E to F. Remember, on your diagram, guys, it's going to be like this if you're using those measurements that we are using. We said we're going to have A, this will be our F, and this will be our G. So E is found in between what? A and F. So we're just going to measure a certain distance there, which will be 2.04 centimeters. Then going up the remaining distance, that will be of A to E, because we know that EF is for the what? Stator copper loss at standstill. While is the A to E, the rotor copper loss at standstill. So that is it. So you just need to be very careful on the presentation that you are going to have. So with this information, guys, let us have our diagram. So here, everything is now clear. So we said EF is, we got 2.04, something like that. Okay, so that is it from that information. Then the full load part, we are going to use it at the end. So that is the last part of our diagram, that one. All right, so let us see what we are given here. All right, so me not to forget, let me just write 90 here, okay? No problem, don't worry about that one. Let us have, so what we're gonna need in this case, we need all the instruments, and you must actually know how to use each and every instrument, guys. Just try to practice in as much as you can. But for those who we have been into, maybe you are doing also those subjects such as drawing, you find out that it will be easier. But it's not that much, guys. Just make sure you go through the basics of your constructions. That can help. So remember, we said the vertical axis is our reference this time. So that is our vertical axis, or V is our reference. So remember, those are lagging power factors. So the current definitely will be this side because we are having voltage. The current is lagging. That is why we are seeing our values being taken this way. For those maybe that would be wanting to understand why is it we are taking our values this way. The current is lagging the voltage. So the first part is for the no load. We have got for the no load here, 82 approximately, 82. So we need to measure 82 from what? From the reference. So remember, guys, from the reference. So this here is supposed to be on the origin there. Close the origin, close this side. So 80 degrees, you mark where the 80 degrees is, all right? So 80 degrees is going to be approximately at this point here where it is straight at 100 there, all right? Just mark a point, just mark a point there. This is our 80 degrees, all right? So that is, we can join this one. Okay, let's just try to see from the origin to this point. So this is our 80 degrees, something like this. All right, so that was going to be, okay, let's just try increase a little bit here. So we're going to have something like this, okay? So that is at 80 degrees. This is the part of our 80 degrees. Representing the part of our open circuit. Remember, this is for our open circuit. The distance between, for that corresponding vector for the open circuit, that is O to O bar, 2 centimeters. So meaning to say you are going to measure 2 centimeters from the origin along that line. You measure 2 centimeters. So according to mine, my 2 centimeters is approximately here. So I'm just gonna mark a point which is here where my 2 centimeters is. So meaning to say I have the corresponding point, which is what? Which is O bar there. 2 centimeters. And along that line, we know that we need what? The referred line that is along horizontally given. So that one, just use your ruler, guys, straight. You have a horizontal line parallel to the one that we are having on the ground. Remember, we've got this one on the ground. So it must be parallel to that, straight. All right. So that was going to be something like this. This must be exactly parallel, guys, to that one. It's supposed to be, all right, maintaining equal distance in between. So this is something that we're going to have from the referred value. Okay, so that is it. This one, we can even reduce it. It is no longer important. Let us just take this one down. Another step from the short circuit, we have got 70 degrees there, and also the vector OA 17,3 centimeters. So we're going to measure first the angle, approximately 70 degrees. Okay. So that's approximately 70 degrees. So this is our 70 here, which is across 110. Just gonna mark a point aside. Okay. So that is the part of our 70 degrees. So this one, it is already constructed. All right. We do not want that construction. But anyways, you are going to, after that 70, you draw the line just like the previous case. So here, this ruler of mine, it can also give me the angles. If I do it like this, so 70, I'm just going to need 70 minus 20, something like this. All right. So this is our 70 degrees. This angle that I'm taking right now, it represents 70 degrees. And also, we saw that the corresponding line there was 17,3. So along as you are having it, just make sure that you have 17, at least 18 centimeters or 19 centimeters. Do not just have the point taken exactly to 17,3. All right, so you can just extend. So let's join. So this is it. Along the angle that we have for the what? For the 70 degrees that we are given. I mean, it was for the short circuit, angle, which is 70 degrees. So that is for the short circuit. Then we can measure the length from point O to A 17,3 centimeters. We already have that corresponding vector. Remember these properties. So 17,3, that was approximately, okay, let's see. 17.3 is going to be approximately there. You mark the point where you have got your 17,3. That is your point A. So we have got the point A there. Representing what? The short circuit current vector OA. So what are we going to do? From the referred value, that O bar that we are given here, we must join to the what? To the point A. So that one, just use your ruler. Okay, join from the point O bar to the point A like this. You join that distance. As we can see here, it is giving me 17 centimeters. This is according to this graph that I'm using here. You measure according to your graph that you are using. There it is giving me 17 centimeters. Remember, we are going to need half of that one, which is half of 17 is going to be 8,5. So approximately 8,5. I'm going to need that half here, 8,5, 8,5, so that I have an exact graph. So use the measurements that you are obtaining from your graph. Please use exactly what you're getting from your graph. So remember, we need along this output line. Remember, this is our output line. Along the output line, we are going to need the midpoint halfway from O bar to A, half of that, which is this point that I indicated here, half. Where we are going to measure 90 degrees along the perpendicular bisector. So we are going to measure 90 degrees. So you must have the 180 covering from O bar to A along the output line. So place this along the output line. All right. So it must cover the output line like this. All right. Then 90 degrees is the one that we are seeing here. Let's see. Let's just see a little bit. All right. So it must cover our output line. So something like this. Something like this. Our output line is here. So if we are going to take our 90 degrees, and this one you must be careful because that's where that semicircle is supposed to be taken from. So any silly mistake that you do is going to affect the part of our semicircle. So yeah, this is approximately something like this. So our 90 degrees is here. This is where we have got our 90 degrees here. This is straight 90 degrees. You just mark a point. All right. So this one is actually giving us a line that is representing here this 90 degrees. But in this case, let's just hope it is going to reduce up to here. We want to take it up to that line. All right. So this is where our 90 degrees was going to be this one that is written 3, to this one. This is our 90 degrees, this one. From what? From that point that we are given. But remember, this is supposed to be an extended line. So I just hope it is going to be easier. All right. Yes, we can even extend that one. Let's try to extend it this side. So I'm just going to extend this line like this. Okay. So this is our line. Okay. So this one is at what? At 90 degrees, where this line, the perpendicular bisector, meets with the referred line here. That is our point what? Our point C. Where I said the point C is actually just like the center of the circle. So the radius will be from O bar to C. This will be our radius of the circle. So meaning to say we can have the circle drawn. If we take this needle point at C, then we open the distance to what? To the corresponding O bar like this. All right. So this is our radius. So if this is our radius, we can simply draw a circle from there, from that O bar that we are given. We can simply draw a semicircle. Actually, here we need what? A semicircle like this. All right. So this one, okay, this one, it shifted. This one, it shifted. Supposed to give us exactly at that point. Something like this. All right. So this is what you're going to have at the end. So in your case, you must have this semicircle exactly at point A and at point O bar there. At this point O bar here and at point it must cut there. This is to show you that this is exactly at the right place. So it must be exactly like this. You have got what? Your semicircle. All right. Anyways, let us finish on this side. We need from A straight to the ground, a perpendicular line, meaning to say you must have that one at 90 degrees. All right. So you must have this one exactly at 90 degrees to the ground. Okay. So that was exactly to the ground, this one. so that we can locate that point E. All right, so this is it. Remember, from this A, we have got the point F on the referred line. This is where we've got our F, and this is where we have got our point G. So in between, in within here, we are going to have the point E. But in this case, they gave us a condition about that point E, where we have got what? The phase value for the resistance for the stator. So we managed to calculate EF. So use this EF, measure it. You can measure that distance. From F going up, we know that we are going to the point E. So you measure that distance, which was 2.04 centimeters. All right. So you're going to take your ruler, guys. You measure 2.04 is just going to be approximately 2 centimeters, guys. But in this case of mine, I can have that. No, 2.4, 2.04. 2.04 is actually less than, it's actually less than 2.1. 2.04, guys, is the value that, so just approximate 2 centimeters somewhere there. But what you know is that to the values, according to the exact measurement, the length there is what? Is 2.04 centimeters. But there you draw 2 centimeters in case that maybe you want to use it for a calculation where EF is. You use this one that you obtained. Yes, on the graph, you can represent 2 centimeters. It's not a problem. So that is where our point E is situated here. So what are we going to do? Join from the point O bar, this one, the referred value to point E, so that we have got our torque line on that in that case. So from this point O bar to point E like this, that is going to give us what? The torque line. Just like that. So this is what we're going to have at the end. So with this, you must make sure that your values, they are at least in within the required values, that is according to what you're given. They must be in within. All right. So another question, another part now is to represent the line L to K, which is out of the condition of a full load. Remember, we are given that we are dealing with what? A full load. So we talked about this in our last class, where when you're dealing with a full load, we're going to have a tangent from the origin to the what? To the semicircle. We must have a tangent. Where the tangent meets the semicircle, that's where we've got our point L. All right, let us just go to those presentation. So for a full load, you must draw a tangent to the what? To the semicircle from the point O. That is a tangent, a line which just touches the semicircle at a single point. All right, so that's a tangent. It's going to be something like this from the origin. All right, so it must just touch the curve at one point. Okay, something like this. Okay, something like this. That's a tangent, this one. So you must place your ruler in a way that you must draw something of this nature to just touch the circle at a single point. Okay, something like this. So it must not enter the circle, it must just touch the circle. So this is in between here, approximately here. This is where we have got our tangent. So where that tangent touches the semicircle at this point, that is our point L. So you're going to take that to the ground, straight to the ground. So use your ruler, straight to the ground from L, straight to the ground at what? At 90 degrees. So that is at what? At 90 degrees. So this is what we're going to need from point L to the ground. that is LK. Remember, we say this will be our point K. And in between L to K, there are some points that we are going to name, which are along the line of LK here, along this line LK. But they must be from the referred value, this O bar, this one. From O bar, we are going to have the first line, this one here. This is the first one on the output line. So that if that point is going to be our M. From this O bar along this line, along the Toki line, that is where we are going to have what? Our point N. From that O bar along this referred line, this one, that is the parallel, the one that is parallel to the horizontal line on the ground. This is our point J, something like this. So these are the points that you are going to have. M, N, J, and K. From what? From the referred. This one, this one, this one, and this one. So the one that is from the origin, this one, is not used. There is nothing that you name there here along this one. You do not name anything. You name these ones which are from Oba, these ones. From Oba here. This one, and this one. So that's it. These are the points that you're going to have. These are the points that we are going to simply have. So we are done. This is our graph. This is the circle diagram in complete. So we can attempt our questions after this. We can attempt our questions. All you just need is to measure what is being asked, the corresponding part, and the formulas. Remember all these formulas. I gave you guys this part of interpreting our circle diagram. So these are the formulas that I'm going to be using, all these formulas that are here, and their interpretation, what each line segment represents, is also given here for those who will be needing to go through. So you must know what the line segment represents, and you must know the corresponding formula for each and every part that we are having. So let us answer our questions. The first question, it was to calculate the power factor. That is our A. So the power factor, from the formulas that we have there, we can simply have our power factor. Remember, power factor, guys, is the ratio that we are going to have, which actually gives us the cos of phi at the end. But that ratio, it was actually taken from I cos phi like this over what? Over current. But instead of us working with these, it can be taken from the line LK over what? Over OL. That is it. So the line L to K, remember, you're summing up everything. L to K. Over what? From O to L, which is our line current. So that is the formula that we are simply going to need. So you measure the distance from L to K, approximately, that was going to give us 5.2 centimeters. Then the length of OL, it was approximately 6.2 centimeters. So that was going to give us 0.839. Remember, for this power factor, guys, the current is what? Is lagging the voltage, all right? So that was our corresponding power factor. The other question that we are given is the rotor input. So from our formulas, guys, the rotor input is affected by the line Ln. So that's square root of 3 times the line voltage times the line Ln. Remember, the part of L to N. We talked about this, guys, on the introduction, what it represents. That's everything on the rotor in the input, all right, which is not, it's not at standstill, this one. Remember, we talk about the issue of standstill. This one is not about the standstill. 380 rated value, 380 times the line Ln, you measure it. So approximately that was 4.6 centimeters. Wherever the vector is, you must multiply by what? By a scale when it is a product like that. You multiply by what? By the scale. 1 centimeter to represent what? 6 amps. That is our scale in that case, all right? So that was going to give us 18,165,749 watts. This is power measured in what? In watts. So that's our rotor input. Moving on to the other question, see the rotor copper loss at standstill. So the rotor copper loss at standstill, we must work with what? The value of the standstill, the rotor part, which is from A to E. So you're going to measure that. So this was going to be square root of 3 times our line voltage times, we say the vector AE. So that's it. Square root of 3 times 380 times our vector AE. You measure the length. That was approximately 3,3 centimeters. So we multiply by the scale 1 centimeter to what? To 6 amps. Just like that. So that was going to give us 13,031,95 watts. So that was our rotor copper loss at standstill. At standstill. Another part of the question, it was now to determine the mechanical output. That is, whenever we are given to calculate the mechanical output, they want you to calculate the rotor output. This one, it is the rotor output at any condition, not at standstill, at any condition. So remember the rotor output at any condition. We say the formula is square root of 3 times VL times LM. So guys, we've got the formulas. Everything is now direct. 380 LM, you measure that, it was going to be approximately 4,3 centimeters times the scale of 6. So that's it. That was 16,981,026 in what? In watts. So that was the mechanical output, the rotor output. Okay. Right. So guys, everything just went upside down. Let me just try to finish it on this other side. I just hope gonna be able to see it here. So these are the effect of these boards, guys. But I just hope we can see on this other side. I'm just gonna use the values. You can measure those values just to finish up. So that was it. Then the part of the efficiency of the motor. That was the E part, the efficiency. So as a percentage efficiency, we can take it from the output of the rotor. Remember, we said we can have this one from the rotor output over the input to the motor, over the input to the what? To the motor. So the rotor output, that is LM, over what? The input to the motor, not to the rotor, but to the motor. That is the whole of what? Of LK. So that's it, times 100%. We're going to have percentage efficiency. Measure LM, approximately 4,3 centimeters. LK, approximately 5,2 centimeters. Then multiply by 100%. So that was going to give us a percentage of 82,692. Right? So that's it. This is what we're going to have at the end. Then the last part was to calculate the torque developed. The torque that is what? Developed. So the torque developed, there are actually two formulas for that. We can calculate it from the rotor output. From the rotor output, you must use the speed of the rotor. If you are working with the rotor output, the speed that you work with is the what? Rotor speed. Or this same torque can be calculated from the rotor input. But when it is calculated from the input of the rotor in this case, the speed that we are going to use must be the synchronous speed. So in this case, we calculated the rotor input on B. The rotor output, we also calculated it when you calculated what? The mechanical output. So you are going to use anyone that you want. Anyone. But we do not have these corresponding speeds, the synchronous speed, the rotor speed. But remember, the synchronous speed can be calculated. We have given a 4-pole. That is the pair poles. It's going to be 4/2, which is what? Which is 2 pairs. And we also have a frequency there of what? Of 50 hertz. So meaning to say the synchronous speed can be calculated. Remember, guys, I talked about this. 60 times frequency. It's going to be 60 times frequency over pair poles. So the 60 times frequency, 50 hertz over pair poles, which is 2. So that was going to give us the synchronous speed of 1,500 revs per minute. Remember, we talked about these formulas on the introduction part. So that was going to help us to calculate the torque because we have or we calculated the input to the rotor on B. So you take the value that you calculated on B, that was 18,165,749. If you still remember this value, everything over 2 pi times the speed in revs per minute. Our synchronous speed, 1,500. So that was going to give us the torque. From this value, you're going to obtain 115,647 Newton meter. Remember, our torque in what? In Newton meter. So that is it. This type of equation, it is actually in your hands. Or you can work with the rotor output. But this one was going to be lengthy because you are going to need the speed of the rotor. This was the synchronous, remember? So how do we calculate the one for the rotor? Remember, from the slip, slip is equal to the synchronous speed minus the rotor speed over what? The synchronous speed. So we need this one. Yet we do not have the slip as well. So you're going to be forced to calculate the slip first. From where? From the diagram now. Remember, slip is rotor copper loss over rotor input. So from the rotor copper loss, Mn over the rotor input, which is Ln. Remember those dimensions, guys. So we're going to measure, this was approximately 35 millimeters, which is 0.35 centimeters. Ln, approximately 4.6 centimeters. So we're going to get a slip of 0.076. So this is our slip, which we can use here to calculate what? Our rotor speed. So we can just substitute or make any the subject. It's up to you. Our slip 0.076 is equal to the synchronous speed. We calculated this 1,500 minus the rotor speed over the synchronous speed, 1,500. So just cross multiply. That was going to help us in this case to eliminate one or two things. So if we cross multiply 0.076 times 1,500, that was 114, which is equal to 1,500 minus n. 1 times this guy is just going to remain as it is. So we need n. We can take it to the other side. So n is equal to 1,500 minus what? Minus 104. So that was 1,386 revs per minute. Remember, we are dealing with this one in revs per minute. So definitely our answer is going to be in revs per minute. So we have the rotor speed here. So we are going to use it. to calculate our torque at the end. So with this formula, like I said, the rotor output is the one that you calculated on D. This one, our mechanical, remember that's our rotor output. So we calculated that one. That was the 16,981,026. Remember your values over 2 pi times our rotor speed, 1,386, just like that. So that is how we can have these values. This type of a question will be in your hands. You can answer it anyway. So this is another way that we could have calculated our torque. So this value for torque was going to give us 116,996 Newton meter, like that. So as you can see, it's just approximately the same, just a little bit different. So you work with any formula, they mark according to the formula that we have used. So do not worry about the difference in terms of the values, that they are not exactly the same. They mark this one according to the formula that we have used. So let's do revise as many questions as we can, prepare ourselves for the exams which are ahead of time.